Welcome to the Calculus, a collection of micro lectures, video lessons, and sample exercises. Let us prove the rule for the derivative of sine function. Here we are going to show that the derivative of sine x, our sine function, is equal to another trigonometric function, cosine x. In order for us to do this, we are going to use the definition of derivative, and we're going to use some important concepts surrounding trigonometric functions. This notation here is also known as the derivative of sine x, which gives us cosine x. Or in other sense, if f of x is equal to sine x, then the first derivative is cosine x. We are going to show this by using the definition for the derivative, being by f of x, its derivative is identified as the limit of f of x plus delta x minus f of x all over delta x as your delta x approaches to 0. So we're going to show this relationship before we apply it on several situations. Of course, other sources would like to use this, that the limit of f of x, plus h in this case, minus f of x over h as h approaches to 0. They are just the same. The other resources just uses h for easier manipulation, but let me use the original form here. Again, we're going to show this relationship. So here is the proof for such. Let us have our f of x being sine x. In short, the first derivative using a definition will follow the limit of sine of your angle x plus delta x minus sine x all over delta x as your delta x approaches to 0. Take note that our notation here is now our function is sine x. So integrating this on the original form, so we will have this form here. Please take note of that. Now, what we need to do here is look closely into this form. I'm going to take this out. I'm going to place it here. The sine of x plus delta x. Because our goal later on is to make sure to remove this or make sure to apply algebraic operations so that this will not be found on denominator, because as this approaches 0, we will have an undefined form. So what happens here is we have this form here because we cannot just simply subtract them just like that because we have two functions here. Now, this is actually considered as one of the sum formulas for trigonometric functions. Please do review that. Given that if we have the sum of alpha plus beta, this gives us sine alpha times cosine beta plus cosine alpha sine beta. This is its identity in our topic for the trigonometric identities. That would mean using x and delta x, this could mean here that we will have equality to sine x cosine delta x plus cosine x sine delta x. And let us try to substitute that on our given. So we'll have here the limit of this equivalence. You will have sine, or let me place it here at the bottom so that I have more space. The limit for this is this equivalence. You have sine x cosine delta x plus cosine x sine delta x, then minus the remaining function sine x all over delta x. Okay, so as delta x approaches 0, let me rearrange some terms so that I will move this a little bit closer here. Sine x cosine delta x, I have here minus sine x, then plus cosine delta x, that's cosine x sine delta x all over delta x here as delta x approaches 0. I'm moving that because I have here common trigonometric function for which I can take out. Okay, I can take that out, leaving this form now. I have the limit of sine x. Then what remains here is cosine delta x minus 1. And here plus cosine x sine delta x. Just like that. Okay? These are all under the delta x. Okay, I have here two terms on my numerator, and it follows this idea that if I have 1 plus 7 over 4, this could be written as 1/4 plus 7 over 4, meaning I can separate this into two different fractions with the same denominator as this, but separating the terms of the numerator following the operation here. So in short, I can rewrite this next form into this. I have here the limit of delta x upon 0. I'm writing that first. I will separate this into two different forms, say with the same denominator. I have here sine x times cosine delta x minus 1 over delta x plus cosine x times sine delta x over delta x. Okay, so I'm separating them into two different terms having the same denominator. Because the next thing here is I could apply the limit theorem, which tells us that the limit of the sum is equal to the sum of the limits. Hence, I can distribute that here and here, giving us this form: the limit of sine x times cosine delta x minus 1 all over delta x as delta x approaches 0, plus the same limit as delta x approaches 0 for cosine x and sine delta x over delta x. So this is another limit theorem. And we also have another limit theorem, and let me use that because we have here product of two different terms, as I would like to pair this and I would like to take this here. So we have the limit of the product is equal to the product of their limits. In short, I can distribute the limit here and here as well as here and here. Therefore, I will have this next form: the limit of sine x as delta x approaches 0 times the limit of, you have here, cosine delta x minus 1 all over delta x as delta x approaches 0. Then that's for the first term, plus for the second term doing the same, the limit of cosine x as delta x approaches to 0, and we have here times the limit of sine delta x over delta x as delta x approaches to 0. So we have four separate terms now, or separate limit expressions, but we have two terms, two pairs of product. Let me copy this as I move to the next page because I need another page here to finalize the result. Let me paste it here. Okay. At the same time, let me move back here and copy this as well as the definition and our target. Pasting that here as well. Okay, let me remove some unnecessary scribbles, this second version, and let me cut this out as I move that here. Take note, this is our target. We need to show that all of this will just result to cosine x. Okay, and that from here we're going to use this. Now, take note that we are trying to solve for the limit as the delta x approaches to 0. But since this first function does not delta x, so it will be treated as a constant. So that would be equal to sine x itself. Times. What is this, by the way? Okay. Take note that in our previous discussions on limits, we have special functions. Actually, two of them are here. I would like to highlight this and this here. Okay, let me write here the special functions that we have learned before. We have two special functions. One minus cosine theta, or in the previous discussion is t over t. If we're going to look for the limit of that as t approaches 0, this special function, that's equal to 0. Please try to review the playlist for limits and continuity. We have a proof for that. At the same time, the limit for sine t over t as t approaches to 0 as well, this is equal to 1. These are special functions we have learned for specific videos, and they are actually just equivalents of this. Because this here, if we're going to interchange the notation of the numerator, we have here the limit of -1, okay, plus cosine delta x over delta x as delta x approaches 0. If we take out negative number, so we'll have here a negative value, or we can take, yes, negative value of 1 minus now cosine of delta x as delta x over delta x as delta x approaches 0. By the limit theorem, you can take this out here, but nevertheless, as you take the limit of this form with the same angle as your denominator, in short, this t and this here, this is equal to 0. This here. In short, the limit of that is 0 itself. So no matter whether this is the form or this interchange, whether negative here, negative times 0 is 0, this entire form is equal to 0 times 0. Okay, that's enough for the first pair. Now, let's continue. You have here plus the limit of cosine, because it doesn't have delta x here, of course, cosine x. And here comes another special function, this one here. Okay, similar, you have here the angle and your denominator, same as this, the angle and denominator, the limit of that as this approaches to 0 is equal to 1. So this is equal to, this is equal to 1, so that means it's equal to 1 here. So finally, as we complete this, we'll have sine x times 0 is 0, plus cosine x times 1 is cosine x, hence this is just entirely equal to cosine x. So we're able to use special functions here as well. And what is this, by the way? As you can see, this is f prime, or the first derivative here. So basically, we have proven, therefore, by this proof, okay, if f of x is equal to sine, f prime of x is equal to cosine x, or therefore, the notation here is the derivative of sine x is equal to cosine x. This is the proof of the derivative of sine being positive cosine x. Now that we are done with this, we can use this now to solve for the derivative of functions involving sine function. Thank you very much for watching. So what are you waiting for? Subscribe now.